Hello, Geography 231 students. Welcome back to tutorial. We haven't had a tutorial in a few weeks, primarily because you had basically 3 weeks of using the same textbook, handouts from a textbook that just basically relied on the same tasks of using the supplemental instructions and all of that. But this week, we've got something different for you. This is a lab that essentially was taken from an Esri lab that deals with OLS regression, which hopefully at this point you've already gone through the lecture, and so you know what OLS, ordinary least squares regression, is. This is not the video to watch if you haven't done that yet. So make sure you first watch the lecture video and go through the lecture notes so that you have a very clear understanding of all the various components of OLS, not least of which are the 6 steps to check your regression model. So you want to make sure you get through that. But assuming you've got to that point already, you are now ready to do this week's lab, and I want to actually walk you through at least a portion of the first single variable model, if not the entire thing, and just so you get a better understanding of how this all works. And it's not that these tasks are challenging, it's more that OLS itself is slightly challenging, and basically the information that you get from the model, yes, it does create spatial data, and yes, you are going to be able to see it on the map, but really the important information from an OLS regression tool are the details that are provided, the R-squared data, the probability, all the various data that come out of the tool itself. So it's not so much about making a map, it's about learning information about the actual regression line. So with that said, let me pick up where we are. So we're doing use OLS regression to locate variables. That's the name of this week's lab. And I'll just read the intro here. So for this lab, imagine yourself in the role of a mayor or city manager. Suppose your community spends sizable public resources responding to 9/11 emergency calls. Projections show the population of your community doubling over the next 10 years. You have questions about how population growth will affect your community's resources and ability to respond to 9/11 emergency calls, 911 calls. Can you more efficiently situate your police and fire stations that respond to 911 calls? Can you do anything to reduce the number of 911 calls that you receive? And can you implement policies now to help you better manage 911 calls in the future? So these are all questions that you might be asking if the responsibility to situate the 911 first responder stations falls on your shoulders. You want to try to streamline response times, make them as short as possible, make the responses as efficient as possible. So how do you do that? Well, you could obviously look at the data and try to draw conclusions from the data with various GIS techniques. There are many different routes you could take. You could do network analysis, you could do buffers, there are many things you can do with GIS. In this case here, what we're looking at are the actual causal factors, the independent variables that affect a dependent variable, in this case 911 emergency calls, the actual number of calls. So what we're going to do here is use OLS regression, which is, again, ordinary least squares, which is one of 2 regression tools that we're going to be discussing this week and next week. So anyway, back at it. So in the following lab, you'll use regression analysis to help determine the causes of 911 incidents in Portland, Oregon. The location doesn't really matter in this case. First thing you need to do is make sure that you download the data from Canvas. So I will assume that you've already done that at this point. If you haven't, go ahead and pause your video, go back to Canvas, the week 12 module, and download the data. Next thing you're going to do is unzip it, save it to your C drive, and then open up the regression pro prj.aprx file. So in the past, we've been opening Arc Pro first and then creating a project. In this case, the project already exists. So once you've got it downloaded, you just go ahead and double click on regression pro.prj. I already have it open. But if you need to open yours and wait a second for it to load, you can go ahead and pause the video. Okay, so what we have here is a raster which shows density, and then we have the GI z-scores, and these obviously are based off of the Hotspot analysis tool. Okay, and so essentially you can see that the tool's already been run to find out where the hotspots are. But now we want to find out not just where the hotspots are, but why they're in these locations and what the factors are involved. So this lab assumes several different things. There are a few assumptions that are taken. And the primary assumption I want to mention, I'm going to zoom ahead real quick, is that the factors that affect the 911 incidence time primarily fall on the population size. Okay, so what I'm going to work with you first to do is use population as the explanatory variable, and then on your own you're going to redo the OLS regression model, and you're going to actually do it a multivariate regression model instead of just a single variable. And in that case, you're going to take population and a handful of other variables. But anyway, I just wanted to highlight that. So, all right, so where are we at? You've opened up the APRX. The map opens up to Portland, Oregon. Next thing you're going to do is explore the map of hotspot incidents. So you'll now explore the map of hotspots of 911 incidents in Portland, Oregon. The map shows the results of a statistical hotspot analysis to determine areas with a higher number of 911 incidents. These hotspots are shown in red. You can also see where relatively few 911 incidents occurred. Areas with low intensities of incidents, emergencies, crimes, car accidents, and so on are called cold spots, which we've already talked about in the past week or so. This map allows you to evaluate hot and cold spots relative to 911 response centers, which are shown as these black plus signs here. So these are 911 response centers. Yes, so okay. So in the catalog pane, I'm going to move this out of the way here. 1 second. Okay. So in the catalog pane, go ahead and expand. First of all, you might not have catalog pane open, so make sure you have that open. And if you don't see it, click on the View tab, and then go ahead and click on the catalog pane right there, and that'll bring it up. So once you have the catalog pane open, maximize the Maps folder, and then go ahead and double-click on Regression Analysis. Okay, so this looks a little bit different. This is based off of the same data. Okay, here. So this map shows the same 911 incident data as polygons instead of points. So they've been aggregated to the census block level instead. So each census block includes a count variable representing the number of incidents in each block. The spatial join tool is used to perform the aggregation. If 911 incidents fell inside a census block, the tool will assign them to that incident count. So go ahead and open up the attribute table for 911 incidents. And you can see here, these are census blocks. So there are 87 blocks. And within this data table, you'll see you have population, call rate, which would be calls per some population number. So maybe it's calls per 10,000 or calls per 100,000. Jobs, people by education, distance to urban center, number of renters, number of unemployed, number of businesses. So you can see these are a lot of different data points. Alcohol X, I actually don't know what that is, but obviously relates to some sort of alcohol consumption probably. Foreign-born population, population density, median income, college graduates, low education, FY, not fiscal year perhaps, I'm not sure. At any rate, you've got all these various data points, and so you can start to probably figure out what you're doing here. You're going to now run a regression model and ask which of these data points has the biggest factor. Well, this lab takes as I said before, makes the assumption that population is the key figure here. As the population grows, and it will double over the next 10 years in this area. This is actually around Beaverton, Oregon, which is just to the southwest of the city of Portland. But as the population grows, it's going to put greater strain on the first responders, the 911 incidents response people. So that's basically what the test is going to be. How will population growth impact the ability first responders to get there in a timely manner? So, okay, so next up, we're going to test the population as the cause of 911 incidents. So your goal is to create a properly specified regression model that explains why 911 incidents are occurring. Before doing so, you'll test some variables, including population, to determine how much those variables contribute to 911 incidents. Running the OLS tool can help you determine the key explanatory variables for your model. Okay, so on the Analysis tab, we want to go ahead and open up the Tools. So it's in the Geoprocessing group. Go ahead and click on Tools, and we're going to do a search for ordinary least squares. You can also just type in OLS, by the way. So go ahead and type in OLS, choose your tool, and then you're going to enter the following parameters. Okay, so for input feature class, go ahead and choose 911 incidents. For unique ID field, it's going to be surprise, unique ID. Okay. For output, you can go ahead and call it OLS pop results. Okay, and this is the key step here, dependent variable. Okay, so this is the variable that we're going to be testing. Okay, dependent variable is going to be calls. So we've got our input feature, 911 incidents, unique ID. The dependent variable is going to be calls, like how are the calls affected by whatever you choose as the explanatory variable, which is also known as the independent variable. And in this case here, we're just going to check population, which is called the pop field. After you do this with me, you'll then do it on your own. As I said before, you're then going to do a multivariate regression model. And in that case, you're going to choose a few other data points as well, and you'll see how they each affect the dependent variable. All right, so once you've got pop selected, you can leave output report blank, and then just go ahead and click on run. You know, it looks like I've already done this before, so I'm actually going to call mine OLS results 2. That's why I had that exclamation mark there. Okay, you wouldn't have that, so you can just call yours OLS pop results, but I already ran this before, and I forgot to delete my data from before. My mistake. Okay. Now, if your machine runs a little different speed than mine, maybe it's faster, maybe it's slower, you obviously can pause the video or rewind or fast forward as needed. But once yours is done, you're gonna, I think there's probably a step in here about saying to close the attribute table. Close the attribute table so you can see your map. Okay, so once yours is done, you're going to see the standard deviation for each block, okay, each census block here. You can see those that are above average, right there in dead center, and those that are below average, the blue. Okay, then you got those that are just about average. So that's basically how the standard deviation works, right? So if it's darker red, it's 2.5 standard deviations above the mean. If it's the darkest blue, it's 2.5 standard deviations below the mean, which means that these are significantly above or below the average, obviously. All right, so the residual appears on the map. These are the residual values, excuse me. Residuals are the unexplained portions of the dependent variable. Some of the dependent variables unexplained because you tested only one variable, right? So when you do the multivariate testing, you can see how other variables potentially affect the dependent variable. So next step, you're going to go ahead and click on View Details in the report, and that's going to bring this up right here. Okay, and then the key thing here, make your window a little bit wider because the way that the text is formatted, it's a little bit wonky. And then go ahead and click on Messages. Scroll down. And this is the important information, okay? So we see the intercept, we see the population, coefficient, standard error, probability, robust PR. So this tells you if you see an asterisk on any of these values, that means they are statistically significant. Okay, so watch out for asterisks, and also watch out for the absence of an asterisk, because that tells you that your data points are not statistically significant. Okay, all right, so basically the OLS regression model has been run, and this is the output right here. Okay, all of this data through here. It looks like a bunch of gobbledygook, especially if you left your window smaller, in which case the text really looks out of whack, right? So make sure you widen your screen. And all of this, well, not all of it, most of it will make sense as you work your way through the lab. Bit by bit, we'll sort of pick each of these data points apart. Okay. All right, so you will now work with the 6 checks that are used to verify a properly specified regression model, which is, in other words, a model that you can trust, a model that's actually reliable and actually tells you good information, right? So such a model includes the key explanatory variables associated with whatever you're trying to model. In other words, your dependent variable, in this case, 911 incidents. And you can perform the 6 checks in any order. All right, so if you're reading about OLS regression in a textbook, it might present the 6 checks in a different order than you're seeing now. The key thing to know is that you can do the 6 checks in any order. It's not like step 1 through 6. It's just, you just check each one as you go. All right, so what I have here is check 1, do the independent or explanatory variables help your model? So after running OLS, you might discover that some of the variables that you choose are statistically significant and others are not. You typically keep the significant variables and eliminate the insignificant variables. If you find out that they're not statistically significant, then you know that it's not one that plays a role in affecting the dependent variable. So you can eliminate that from your research, essentially. So in the report, under the summary of OLS results, locate the pop variable and its coefficient. All right, so the coefficient is 0.015920. Is the population variable statistically significant? Well, how do we know? We look over here. We see probability has an asterisk next to it, and the robust PR also has an asterisk. So that tells us that yes, there is a statistical significance to the population variable. Okay. Check 2, are the relationships what you expected? So in addition to checking whether a variable is important to your model, also check the signs, whether it be a positive or negative value associated with a coefficient. So what you want to see, if it is a positive coefficient, in this case here, a positive correlation. So as population increases, so does the strain on the 911 incidents, right? The 911 calls. That's what you would expect to see. So if you see a negative there, then you might think, okay, something is amiss, something has gone awry. So you want to make sure that the coefficient trends the direction you expect it to. So in other words, this would be a positive correlation, not an inverse correlation. Okay, so in the report, locate the pop coefficient, which is right here. Again, it is a positive. It is not a negative. So that means coefficient has no sign, which indicates it's a positive relationship. So that's good. So far, we've got 2 out of 2 have checked out. Check 3. Are any of the explanatory variables redundant? When you choose a variable to help explain something, use variables that tell the, when you choose variables to help explain something, use variables that tell the same story, right? The variance inflation factor, VIF diagnostic tool, helps you determine whether your variables are redundant or not. As a rule, a VIF over 7.5 is not good. So you want to remove those variables one at a time until the redundancy is gone. So because you ran OLS on only one variable, there is no VIF, obviously, because you're only looking at one versus multiple. So again, there is no variance inflation factor, VIF, in this case, because there's only one variable involved. Okay. So check 4, is the model biased? The Jarque-Bera test assesses whether the residuals are normally distributed. When the results of the Jarque-Bera diagnostic is statistically significant, the model is biased or skewed. Okay, so the graphics to the right here show an example of skewed and normal distributions. If it's skewed to the left, it's considered a positive skew. If it's skewed to the right, it's considered a negative skew. What you want to see is a normal distribution, which is just a typical bell curve. Okay. So in your report, you want to locate the Jarque-Bera statistic and the statistically significant probability on the right. The asterisk indicates that the residuals are biased for the population. So we got to find that first. Jarque-Bera. Okay. We see an asterisk. We do. So this is residuals are biased. Okay. So we have to ask how, in which way. Okay. Which you will actually you'll run a test in a bit. Okay, so first we'll do check 5 and then we'll run a test. So a properly specified model must have the correct variables. In the model, you used only one explanatory variable, so you need more variables. Omitting explanatory variables is called a misspecification. Misspecification is a common problem with regression models and can lead to other problems, which often result in failure of one or more of the 6 checks. So let's go ahead and we're going to do a quick spatial autocorrelation, which relies on Moran's I, and that will tell us how the data are, or if the data are clustered or dispersed, or if they are randomly distributed. We already know that they're biased in some way or the other, and so once you run the spatial autocorrelation tool, you'll find out if they are clustered or not. So just move your OLS statistics window, the details window, off to the left. Don't close it. Just move it so that you can get to the geoprocessing pane, and click this back button here, and then do a search for spatial autocorrelation, global Moran's I, and go ahead and open that up. In this case here, again, we're going to find out how our data are biased. Are they clustered, or are they dispersed? So in the input here, we're going to choose the data set that we just created. So in your case, it'll be OLS pop results. Mine, again, has the 2 at the end because I didn't delete my original data. For the input field, choose residual. For generate report, go ahead and check that. And then you can leave the remaining 4 inputs as the default. Okay, let's go ahead and click run. And once again, you're going to have the details here. If you just put your cursor over it, you'll see this window pop up. But if you want it to stay, then you want to go ahead and click on view details, and then maximize that window so you can see it better. And then this is just like a couple of weeks ago when we were running our various statistical analysis tools. You're going to see the report file link. So go ahead and click on that report file, and it's going to open up in a window. And you will see that the z-score is very high, okay? And so it falls in statistically significant cluster, okay? So the data are statistically significantly clustered. It's red. That's a main reason, and also the z-score is high. Okay, so if it's above 2.58, then you know that it has a very high probability of being not randomly distributed. So in this case, clustered. Okay. So given the z-score of 6.593409, there is a less than 1% likelihood that the clustered pattern could have been the result of random chance. Okay, so now we know, if we go back to our checks from before, we see that, okay, the data is skewed, right? It's not, there's no typical bell curve, not a normal distribution. It's a skewed distribution, positively skewed, and now we know it's because it is clustered, right? Okay, so you can go ahead and close that window and return to ArcGIS Pro. So the last check, the last of the six checks rather, is how well are you explaining your dependent variable? Okay, so the last check evaluates the model performance. There are 2 values to consider: adjusted R-squared and the Ikeiki information criterion. Ikeiki was he actually just passed away about 10 years ago. Was a mathematician essentially, and he more or less is known for coming up with this particular information criterion check. Okay, so the adjusted R-squared value is important, but the value alone cannot be trusted unless other checks are passed. The values for adjusted R-squared range from 0 to 1, and essentially they are expressed as a percentage. So if you see an numerical value of 0.81 or 0.81, that means it's a 81% significant in this case. Okay, so it represents this percentage. So look again at the OLS report, which, all right, so hopefully you still have your OLS statistics window available. Let's go ahead and bring that back into the screen here. And then you want to look again at the OLS square report, and under OLS diagnostics, locate the adjusted R-square data. All right. So the adjusted R-square data is right here, R-squared. It is 0.393460. Okay, so adjusted R-squared is always a percentage value between 0 and 1, as I said before. The adjusted R-squared value in this case is 0.393460. It indicates that the population alone explains 39% of 911 incidents. Okay, so for a properly specified model, 39% is a good percentage, but you want to explain more of the dependent variable. So adding another explanatory variable will help. The next statistic will evaluate model performance is AIC. Okay, so AIC, which is located above the adjusted R-squared value, right here, and that's the Ikeiki information criterion, as I said before. In this case, the number is 791, the 791.05. Okay, so AIC measures how well the estimated statistical model fits. AIC is not a test of the model in the sense of a hypothesis test. Rather, it's a tool for model selection. Basically, it tells you more or less how good that model is performing. Okay. So given a particular data set, several competing models might be ranked according to their AIC value, and the model with the lowest AIC is the best. So you always have to keep this one in mind, 791. So when you go and do a multivariate regression model on your own, you will also have an AIC value, and so you'll want to compare the two. Depending on which one is higher, which one's lower, that'll help you determine which is more or less the better model. So we'll say 791, we'll say it's an average score. Could you get a lower number? Potentially, probably by adding more variables, right? So you will compare this AIC value with the value of the next model that you create for the same analysis. The AIC value is always relative. You can tell whether the AIC is high or low only by comparing the AIC value to the model that you're testing, the model that you're testing to another model that tests the same dependent variable. Okay, so obviously, if you're comparing it to a different dependent variable, you would end up with a completely different AIC, and it would not be relevant to compare across, apples and oranges. So after performing the 6 checks on the OLS results, you can see that you do not have a properly specified model. Next, you're going to add more explanatory variables. So you can go ahead and close the autocorrelation and the OLS square windows now. And this is also where I will sign off. And you can now do step 6 of the lab on your own, which is basically doing what we just did, but you're going to, instead of just have population, you're also going to factor in jobs, the low education field, and the DST to urb center, so distance to urban center. So instead of having one variable, you're going to have 4 variables. And then you will find that you probably have a better model, but you need to find out for sure. Okay, so go ahead and run it again. And then once you're done doing that, once you're all through, you're going to want to answer these questions. Okay, so these are posted in the module and also in the lab itself. So you need to answer these questions based off the results of the multivariate model that you're about to do on your own, not the single variable model that we just did together. These are specifically going to be from the multivariate model that you're about to do. Okay, so go ahead and look through those questions, answer them as best you can, and upload your answers to Canvas, and that will be your deliverable for this week. Okay. All right. So on that note, I will sign off and have a great week. Bye-bye.